Wyoming Territory, 27th of March, 1884. A spring cyclone sweeping through the Wind River drainage registered gusts above 70 miles per hour at the Fort Washakie telegraph office. Freight receipts logged overturned sleds. Ranch notes listed 3 cabin doors torn completely free, hinge plates wrenched out of green pine jambs. Most cabins use standard 1.5 to 2-inch plank doors hung on 8 to 10-inch strap hinges, each screw bearing more load than the timber could hold when saturated and cold. But one inspection entry from the Shoshone Agency noted a different result. A 5-inch laminated door held shut by a loose-fit cradle-bar dropping into deep pockets carved into the wall logs themselves. The bar rocked under impact, distributing force into 2 full log courses instead of hardware. The inspection remark was brief. Door held, heavy scarring. The question that follows comes down to numbers, wood behavior, and joinery under real loads. Fort Washakie weather table, monthly temperature and wind records, 1880 through 1884, 3rd of April, 1884. South Fork of the Little Wind, Wyoming Territory. Frost rimmed the interior rafters of a trapper's cabin. Night low, 12 degrees below zero, Fahrenheit. Settlers assumed early spring had arrived. Weather records from Fort Washakie told a different story. January through March, lows had averaged 15 to 25 degrees below zero across the previous 4 winters. The terrain sat between 7,200 and 8,000 feet elevation. Winter winds normally sustain 30 to 40 miles per hour. Spring spikes above 60 miles per hour appeared in multiple documented reports. Most cabin doors depended entirely on hardware. Trading post ledgers from Lander listed number 3 wrought strap hinges, 8 to 10 inches long. Screw pull-out resistance was limited when driven into moist lodgepole pine. Typical cabin walls measured 8 to 10 inches thick, single-wall construction, chinked with clay and straw. The mechanical reality was simple. Hinge systems concentrated stress at a single point. Each screw bore shear load independently. When wind pressure exceeded the cumulative pull-out strength of 4 to 6 screws, the door failed. Temperature cycling made failure inevitable. Moisture swelled the wood. Cold shrank it. Each cycle loosened the screw threads slightly. Over one winter, a hinge installation that started secure became marginal. Fort Washakie damage reports listed 9 structures with door failures that month. Only one door showed impact scars without structural failure. The difference was not the door itself, it was how the door connected to the wall. Lander Supply Depot Ledger. Itemized sales records, May 1883. 10th of May, 1883. Lander Supply Depot, Wyoming Territory. Grit caught in hinge knuckles sat displayed on the store counter, evidence of hardware that had failed in the field. The lumber supply chain was straightforward. Lodgepole pine came from within 2 to 10 miles of most building sites. Douglas fir required hauling 20 to 40 miles. Hardwood for specialized components arrived occasionally by freight wagon when settlers were willing to pay. Costs reflected transport. Hinges sold for 15 to 25 cents per pair. Freighted hardwood cost $2 to $3 per stick. Speed builds favored hardware. A trapper building temporary quarters wanted minimal labor investment. 2 strap hinges could hang a door in an hour. Cutting deep pockets into wall logs required 6 to 8 hours of careful work. But 2 construction traditions offered alternatives to hardware dependence. Shoshone cache structures use slip-fit locking timbers. Load-bearing surfaces spread across wide contact areas. No metal components. Norwegian settler barns employed rocking drop bars. The bar sat in shaped pockets that allowed controlled movement. Under load, the bar shifted slightly, distributing pressure across multiple bearing surfaces instead of concentrating it at fixed points. The ledger from May 18, 83 showed the economic incentive. One line read, hinges, straps, 24 ordered. Merchants moved hardware in bulk. Custom timber work produced no sales. The Cradle-Bar door combined both traditions. Deep pockets borrowed from cash logic. The loose-fit bar used the rocking principle from barn construction. Total material cost, 1 hardwood beam. Labor, less than 1 full day beyond standard door construction. A 3-inch pocket changed the entire load path for less than an hour of additional work per side. Shoshone Agency. Inspection note, Winter Structural Survey, December 18th, 82, 1st of December, 1882. Shoshone Agency Winter Inspection, Wyoming Territory. The door frame showed shrinkage from early winter dryness. Visible gaps appeared at the hinge side, 1/8 inch wide. Archival notes from the period mention barred or cradled doors without detailed description. Technical reconstruction requires combining multiple source fragments. The door itself used 4 to 5 inch laminated planks. 3 layers, offset at the seams for stiffness. Total thickness, 4.5 to 5 inches. The pocket sat 3 to 4 inches deep, cut into opposite log faces at the same height. Precision mattered. If one pocket sat even half an inch higher than the other, the bar would bind instead of rock. Cutting required an axe for initial removal, followed by adze work to shape the pocket floor and walls. Final smoothing used a chisel. The shoulder, the upper edge of the pocket that would bear impact load, needed to be square and solid. Any bevel or irregularity would concentrate pressure and risk splitting the log. The bar itself measured 4 inches by 4 inches in cross-section. Oak or ash when available from freight. Locally, aspen, reinforced with an iron strap along its length. The bar needed to be straight. Any bow or twist would cause binding. Edges were chamfered slightly to prevent sharp corners from catching. Clearance was critical. 1/4 to 1/2 inch of play allowed the bar to rock under impact. Too tight, and it would jam. Too loose, and it would rattle or lift out under the wrong force angle. The mechanical advantage was straightforward. A hinge door resisted force by stiffening. Stress rose until something broke. A cradle-bar door yielded slightly under impact. The bar dropped deeper into the pockets. Load spread across 2 full log courses in compression. Wood handles compression far better than shear. The inspection note was brief. Pocket shoulders bearing strain, not hinges. A flexible lock had become structural armor. Army Hunting Report documented grizzly bear behavior and impact force estimates. Wind River Region, 6th of January, 1883. Wind River Valley, Wyoming Territory. Rim ice thickened on an exposed hinge strap outside a standard cabin door. Wind load calculations were simple. 70 miles per hour wind produced 20 to 30 pounds per square foot of pressure. A typical cabin door measured approximately 7 square feet. Sustained wind load, 140 to 210 pounds. Gust spikes exceeded 300 pounds. Bear impacts presented different numbers. Army hunting reports from the region documented grizzly strikes at 400 to 600 pounds of lateral force. The blow came suddenly, concentrated at a single point. Door planks could absorb that impact if properly laminated. The failure point was always the connection. Screw pull-out strength in green lodgepole pine ranged from 150 to 180 pounds cumulative for a standard hinge installation. 4 screws per hinge, 2 hinges per door. Total theoretical resistance, 1,200 to 1,400 pounds. But that number assumed ideal conditions. Dry wood, screws driven perfectly perpendicular, no cyclic loading, no moisture variation. Real conditions degraded performance rapidly. Freeze-thaw cycles loosened threads. Moisture swelled wood fibers around screws, then contraction during freezing created gaps. Each cycle reduced pull-out strength by 5 to 10%. After one winter, a hinge installation that started at full strength operated at 60 to 70% capacity. Wind didn't pull steadily, it gusted. Each gust applied peak load, then released. The screws worked slightly looser with every cycle. Eventually, one screw failed. Load redistributed to the remaining screws. They failed in sequence. The Cradle-Bar system eliminated shear loading on fasteners entirely. The bar sat in pockets. Gravity held it down. Impact drove it deeper. The pockets converted lateral force into compressive load on the log shoulders. Wood fiber compressed slightly, fractions of an inch, then held. Under identical. Wind conditions, hinge screws failed in minutes. Bar pockets compressed and stopped. The door stayed closed. Hand auger. Boring tool for starting pocket excavation found at abandoned trapline site, 12th of August, 1882. Trapline cabin construction site, Little Wind drainage. Fresh auger shavings lay in a pile beside a newly notched log, evidence of pocket work in progress. Door lamination began with 3 planks, each measured 1.5 inches thick, cut from straight-grained pine or fir. The planks were laid with seams offset by at least 6 inches. Wooden pegs or cut nails held them together. Some builders added a thin layer of pine tar between planks for water resistance. Total door thickness, 4.5 to 5 inches. Weight, 70 to 90 pounds depending on wood density. Pocket cutting required precision. The builder marked pocket locations on opposite walls at identical height. An auger started the excavation, boring multiple holes to remove bulk material. An axe cleared the rough interior. An adze shaped the floor and walls. A chisel finished the shoulders. Depth mattered most. 3 to 4 inches gave the bar full engagement under normal conditions and room to drop deeper under impact. The shoulder angle needed to be 90 degrees. Any undercut would weaken bearing capacity. Any overhang would prevent the bar from seating properly. The bar itself came from freighted hardwood when possible. Oak or ash provided maximum strength and wear resistance. Local aspen was acceptable if reinforced with an iron strap, screwed or pegged along its length. The bar measured 4 inches square in cross-section, length equal to door width, plus 6 inches. Edges were chamfered with a draw knife to prevent binding. The ends were left square to maximize bearing surface in the pockets. Interior jamb reinforcement added final strength. 1-inch diameter dowels were driven vertically through the door jamb logs at 6-inch intervals, pinning them to the logs above and below. This prevented the frame from racking under lateral load. Labor math was straightforward. Door construction, 1.5 to 2 days. Pocket cutting, 6 to 8 hours. Bar preparation, 2 to 4 hours. Hardwood freight from Lander, 35 to 50 miles. Weight 35 to 50 pounds per bar. A standard hinge door could be built in 3 to 4 hours. The Cradle-Bar system required nearly 3 times the labor. But the hinge door would fail within 2 winters. The Cradle-Bar door would outlast the cabin. The slowest part, the pockets, ended up being the part that saved the frame. Cash door slip pin, worn timber locking mechanism from Shoshone storage structure, 19th of July, 1881. Shoshone Agency perimeter storage yard. A cash door's slip pin showed wear polish from years of use, the bearing surfaces smooth and dark from repeated operation. 3 construction philosophies operated in the same territory, each solving the door problem differently. Comparison revealed fundamental differences in approach. Shoshone cache construction used slip-fit timber locking. A horizontal member dropped into carved pockets, similar in principle to the Cradle-Bar, but with different execution. The locking piece often featured carved stops or shoulders that engaged corresponding notches in the pocket walls. Load distributed across wide bearing surfaces. No metal components. The system could be built entirely with stone tools and required no freight materials. Army field cabins followed standard military engineering practice. Doors used 1.25 to 1.5-inch plank construction with diagonal bracing. Strap hinges attached with wood screws driven into the jamb. The diagonal braces prevented the door from racking under its own weight, but did nothing to strengthen the hinge connection. The system worked adequately for temporary structures in controlled settings, but failed rapidly under frontier conditions. Homesteader practice varied widely based on experience and available materials. Most used battened plank doors hung on strap hinges. Clay or mud sealed gaps around the frame. The seal cracked after freeze-thaw cycles, allowing draft and moisture penetration. Repairs required annual maintenance. Many doors sagged within 1 year as hinge screws loosened. The functional contrast was clear. Indigenous systems handled closure and security using timber mechanics and geometry. Military systems handled static loads adequately, but ignored dynamic impact. Settler systems prioritized construction speed over longevity. The Cradle-Bar door borrowed the load distribution logic from cache construction and applied it to a framed door that could seal tightly against weather. It handled both static closure and dynamic impact. The bar's mass, typically 20 to 30 pounds for a 4x4 hardwood beam, provided inertia that damped oscillation. Under wind buffeting, a hinge door would rattle and stress its fasteners. A Cradle-Bar door would rock slightly in its pockets, each movement absorbing energy rather than accumulating stress. No hinge system ever matched the inertia of a 4x4 hardwood bar set deep into log shoulders. The comparison wasn't close. Compression bruised pocket shoulder. Physical evidence of load distribution from impact events. 15th of January, 1882. Winter cabin check. Wind River drainage. A half-inch frost halo surrounded the pocket mouth where interior moisture had condensed and frozen. Small-scale testing occurred naturally through seasonal and accidental loading. The results provided clear data on system performance before the major test arrived. Wood shrinkage at 30 degrees below zero Fahrenheit caused measurable changes in cabin geometry. Logs shrank in diameter. Gaps opened in chinking. Hinge installations loosened as the wood pulled away from screw threads. Standard doors showed visible movement at the hinge side. The Cradle-Bar system experienced the same shrinkage, but the bar simply dropped slightly deeper into the pockets. Function remained unchanged. A documented thunderstorm in summer 1883 provided impact testing. A large branch struck a Cradle-Bar door during high winds. The blow drove the door inward against the bar. Inspection afterward showed compression bruising on both pocket shoulders, dark marks where wood fibers had compressed under load. The bruising measured approximately 1/8 inch deep. The door had held. The pockets had absorbed the impact without structural failure. Snow load created different stress patterns. Heavy snow accumulation on the roof caused the entire cabin frame to rack slightly as the structure settled under weight. A rigid door system would bind or split at the joints. The Cradle-Bar door compensated. The bar rocked in its pockets as the frame shifted. When the snow melted and the frame returned to its original geometry, the bar settled back into normal position. Typical doors showed failure at stile joints where vertical members met horizontal rails. The joints split under racking stress. Cradle-Bar doors showed only surface scars on the outer planks. The laminated construction distributed stress across multiple layers. No single joint bore critical load. The scars did not signal weakness. They marked where the load had chosen to travel. Impact energy had compressed wood fibers in the pockets rather than breaking fasteners or splitting joints. The evidence was visible, but not structural. The door remained functional. Each test event added data. The system worked under cold, under impact, under frame movement. The margin between applied load and failure load remained substantial. That margin would matter when the real test arrived. Lander Trading Post Ledger, sales records showing hardware movement and ordering patterns, 2nd of November, 1883. Lander Trading Post Ledger Review. Ink-faded tally marks recorded hinge orders through the previous 2 years. Adoption statistics showed the economic reality. Analysis of building records from the Wind River and Green River drainages indicated only 4 to 6% of cabins used deep pocket bar systems. The overwhelming majority relied on strap hinges. Multiple factors drove the pattern. Extra labor stood first. A trapper building temporary quarters to work a seasonal drainage wanted minimum time investment. The cabin needed to shelter him through one winter, possibly 2. Permanence was not the goal. Mobility was. 2 strap hinges cost 25 cents and could be removed when he moved on. 8 hours cutting pockets yielded no salvageable value. Heavier components created transport difficulty. A hardwood bar weighed 35 to 50 pounds. A trapper working alone, traveling on foot or horseback, carried that weight across miles of rough terrain. 2 hinges weighed less than 2 pounds. The choice was obvious for anyone prioritizing mobility. Merchant economics reinforced hardware dependence. Trading posts moved hinges in bulk. A single freight wagon from the east could carry hundreds of hinge pairs. The merchant marked them up and sold them steadily. Custom timber work produced no inventory and no sales. Store owners had no incentive to promote methods that eliminated hardware purchases. Cultural factors mattered as well. Trappers and early homesteaders measured themselves partly by construction speed. Building a functional cabin in 3 days proved competence and toughness. Taking 2 weeks to build the same thing with extra features suggested excessive caution or lack of confidence. The mathematical paradox was clear. The Cradle-Bar system cost almost nothing in materials. 1 hardwood beam versus 2 hinge pairs came out nearly equal in freight cost. It added less than 10 hours to total construction time. It provided dramatically superior performance. Yet adoption remained minimal. The frontier rewarded what appeared quick and mobile, not what survived longest. That preference would reverse when survival margins disappeared. But in 1883, most settlers still believed speed was the right choice. The ledger line read, "Straps, ordered in bulk." The market had spoken. Fort Washakie telegraph log. Storm event documentation with wind speed estimates 27th through 28th of March, 1884, Wind River drainage, Wyoming Territory. Sand and grit blasted loose chinking from cabin walls as the cyclone front arrived. Fort Washakie telegraph records documented gusts exceeding 70 miles per hour. The telegraph line failed repeatedly throughout the storm. Each repair lasted only hours before the next failure. Communication with landers ceased for nearly 2 days. 3 cabins lost doors completely during the first night. Inspection afterward showed identical failure mode. Hinge screws sheared under sustained wind load. In 2 cases, the door frame itself twisted as suction pressure pulled the door outward while internal air pressure pushed outward simultaneously. The door jamb logs separated from the wall logs at the corners. The entire assembly, door, frame, and adjacent wall sections, failed as a unit. 1 cabin lost its door when a horizontal gust caught the door at an angle during a moment when the occupant had opened it to check conditions. The wind wrenched the door completely off its hinges and carried it 30 yards before slamming it against a woodpile. The door shattered. The occupant barely got the opening barricaded with furniture and blankets. The mechanical explanation was straightforward. Strap hinges resisted force through rigid connection. The screws either held or they didn't. Under sustained high wind, the door functioned as a lever. Each gust applied force at the door's center of area. That force multiplied by the door's width created torque at the hinge line. The screws experienced pure shear load. When cumulative load exceeded pull-out strength, failure was instantaneous. The Cradle-Bar door at the Shoshone Agency cabin experienced the same wind loads, but the structural response differed completely. As wind pressure drove the door inward, the bar dropped fully into the pockets. The door began to move, then stopped. The bar had seated against the pocket shoulders. Further inward movement compressed wood fibers in the bearing surfaces. The compression distributed load across 2 full log courses. The logs themselves handled the force as pure compression. Wood is strong in compression, hinges sheared in seconds. The cradled door started to move and kept holding. The difference was not strength. It was where the force went and how the material accepted it. Pocket shoulder scrape marks. Physical evidence of bar movement under extreme load, 29th of March, 1884. Post-storm inspection, Shoshone Agency cabin. Scrape marks on the pocket shoulders measured 1/8 to 1/4 inch deep, darker than surrounding wood. The impact sequence could be reconstructed from physical evidence. The storm had driven the door inward against the bar. The bar, initially resting near the front edge of the pockets, was forced backward and downward. The bottom edge of the bar scraped against the pocket floor as it moved. The upper edge compressed against the pocket shoulder as load increased. The rocking motion was critical. As the bar shifted, it maintained contact with both pocket surfaces simultaneously. Front edge lifted slightly. Back edge dropped. The geometry created a wedging action. The harder the wind pushed, the more firmly the bar wedged into place. Increased load improved seating rather than approaching failure. The laminated door construction contributed essential stiffness. 3 offset plank layers prevented the door from flexing as a single panel. Flex would have changed the load angle and potentially lifted the bar out of the pockets. The rigid door maintained consistent geometry throughout the impact. Peak load occurred during the strongest gusts. Wind pressure probably approached 350 to 400 pounds for periods lasting several seconds. That load transmitted through the door planks into the bar. The bar transmitted it into the pocket shoulders. The log courses above and below the pockets absorbed the force. Compression damage in the pockets told the story of load distribution. The darkened marks showed where wood fibers had crushed. Measurements indicated approximately 1/8 inch of compression at peak load. For comparison, the bar had over 3.5 inches of remaining engagement depth. The system operated well below its ultimate capacity. Hinge-based doors failed from stress concentration. All force channeled through a few screws and the small contact area of the hinge plate. The Cradle-Bar system distributed force across bearing surfaces measuring 16 square inches per pocket, 32 square inches total. Surface area mattered. The physical principle was elementary. Pressure equals force divided by area. Identical force spread across larger area creates lower pressure. Lower pressure stays below material failure threshold. The door survived not because it was stronger, but because it was smarter. Where hinges concentrated force, pockets absorbed it. The evidence sat visible in compressed wood fibers that would bear load for years to come. Claw-scored door plank. Bear damage documentation showing impact without penetration, 14th of April, 1884. Agency cabin inspection, 2 weeks after the cyclone. 4 parallel claw grooves crossed the outer plank, each approximately 3/8 inch deep. The inspection notes confirmed bear activity. The animal had approached the cabin, probably attracted by food stores or simply investigating a structure in its territory. It had struck the door at least once, possibly multiple times. The claw marks showed the strike angle and depth. Load estimation for bear impacts came from Army hunting reports and trapper accounts. A large grizzly striking with one forepaw could deliver 400 to 600 pounds of lateral force. The blow was sudden, not sustained like wind load. Impact duration measured in fractions of a second. The door had absorbed the blow without failure. The outer plank showed surface damage, the claw grooves, but no structural compromise. The laminated construction distributed the impact across all 3 plank layers. The bar remained seated in its pockets. Comparison cabins in the area told a different story. 2 cabins with standard hinge-mounted doors recorded bear damage during the same period. Both showed splits in the lower door stiles where the horizontal impact had exceeded the joint strength. 1 cabin's door latch had broken completely. The occupant had reinforced it with a wooden bar propped at an angle from floor to door, an improvised backup system because the primary closure had failed. The Cradle-Bar system showed compression evidence again in the pocket shoulders. Additional darkening indicated the bar had been driven deeper during the bear strikes, but the pockets themselves remained intact. The log structure had absorbed impact that would have torn standard hinges free. The mechanical margin was revealing. The storm had proven the engineering under sustained load. The bare clawing proved the reserve capacity under sudden impact. The system had handled both. Most cabin doors faced either wind or animals, rarely both within 2 weeks. This door had survived the combination. The storm proved the method. The claws proved the margin. The method that settlers had called excessive and wasteful had proved exactly adequate for conditions that standard construction could not survive. Wyoming Ranch Manual. Construction reference document mentioning load-spreading bar systems. 1890 through 1894. High wind districts of Wyoming and Idaho territories. A sun-cracked ranch ledger sat on an office shelf, its spine broken from decades of reference use. Adoption patterns after 1884 showed geographic concentration. Cradle-bar door construction remained localized to drainages with documented high wind exposure. The Wind River Valley showed 15 to 20% adoption by 1890. The Green River drainage with similar wind conditions showed comparable rates. Low-elevation areas with moderate wind saw minimal adoption. Ranch construction manuals published in the 1890s referenced rocking bars and load-spreading braces in door construction sections. The descriptions remained brief, 2 or 3 sentences, but their inclusion indicated the method had achieved recognition beyond individual builder knowledge. Maintenance records provided the clearest evidence of performance advantage. Repair logs from ranches using cradle-bar doors showed 70 to 80% fewer door-related maintenance entries compared to hinge-based systems. Fewer repairs meant less labor, less material cost, and less interruption of daily operations. The economic benefit accumulated over years. Settlement retention patterns showed correlation with construction quality. Communities where cradle-bar and similar robust building methods became standard practice showed higher rates of continuous occupation through difficult seasons. Families stayed where infrastructure worked. They left where repeated failures made survival too difficult. The method never achieved widespread adoption. It remained a regional solution to specific conditions. Settlers in areas with moderate weather continued using standard construction. The market for hinges remained strong. Trading posts continued ordering hardware in bulk. But in the high wind valleys where winter could kill and where bears tested every structure, the cradle-bar door became standard practice among builders who intended to stay. Temporary trappers still used hinges. Permanent homesteaders cut pockets. The cabins that stayed standing determined who stayed settled. Infrastructure shaped demographics more than any other single factor. Good doors meant families survived winter. Families that survived winter filed successful homestead claims. Successful claims built communities. Communities attracted services. Services enabled growth. The connection between a rocking bar in 2 pockets and the pattern of settlement across Wyoming Territory was direct, documented, and undeniable. Recovered cradle-bar, 4x4 hardwood beam showing compression bruising and decades of use, 1931. Collapse survey of abandoned trapline cabins, little wind drainage. A 4x4 hardwood bar lay beside the ruins of a cabin, warped by moisture and time, but structurally unbroken. The survey team documented the find. The bar showed compression bruising on its upper edges precisely where contact with pocket shoulders would have occurred. The bruising pattern matched the load geometry described in earlier records. Dark compression marks, approximately 1/8 to 3/16 inch deep, ran along both edges for most of the bar's length. The cabin itself had collapsed decades earlier. The roof had failed first, allowing weather to rot the wall logs. The door planks had separated as the laminating pegs rusted away. The pockets in the wall logs had eventually deteriorated as water infiltrated the exposed end grain. But the bar remained sound. 60 years of exposure had warped it and weathered the surface, but the core was solid. Hardwood oak, based on grain analysis. Probably freighted from the east in the 1880s. It had outlasted the structure it was built to protect. The survey report noted, Door construction differed, failure not evident. The technical language understated the finding. The door had not failed. The cabin around it had failed. The difference was instructive. The principle that emerged from 50 years of frontier building records was consistent. Systems that adapted to pressure, not those that resisted rigidly, left the clearest survival record. Flexibility under load, distributed bearing surfaces, and material properties matched to force types determined which structures stood and which fell. The Cradle-Bar door exemplified the principle. It moved when struck. It distributed when loaded. It compressed rather than sheared. Every aspect of its design worked with material behavior instead of against it. The frontier sorted builders as ruthlessly as it sorted settlers. Those who understood how forces actually moved through structures built cabins that lasted. Those who relied on assumptions built cabins that failed. The hardwood bar lying in the collapsed ruin had done its job for longer than most frontier structures stood. The compression marks proved it. The survival of the bar itself, decades after the cabin fell, proved it again. Designs that yielded left records. Designs that resisted left ruins.